In part four of the lecture today, I want to talk about soil engineering properties relating to landscape planning. And in this component, I want to talk about bearing capacity of soils, shrink swell capacity, risk of corrosion, potential frost action, angle of repose, and some dimensions relating to erodibility. Bearing capacity of soil refers to the capacity of the soil to support loads that are applied to the ground. As you can imagine, this is a very critical dimension because inherently in the urbanization process, in any building process, we are adding weight to the surface of the land. And as we add weight to the surface of the land, the soil is the first element that is encountered and that must be able to withstand the force that's being applied to the land itself. So different kinds of geologic and soil materials have varying levels of bearing capacity. Bearing capacity is measured in allowable bearing value in terms of tons per square foot. What is the bearing capacity of soil? How many tons per square foot is the soil or geologic structure able to withstand before it crushes? And we can see in this table that when we move from massive crystalline structure down to sedimentary rocks, we're seeing a significant reduction in bearing value, bearing capacity. Massive crystalline bedrock, granite and gneiss, for example, is able to handle a bearing value of 100 tons per square foot, whereas sedimentary rocks such as shale or sandstone crumble at about 15 tons per square foot. We can apply the same concept to soil bearing capacity and talk about well compacted gravels and sands, which have a lot of larger particles within them uh, uh, and are pretty heavily compacted, being able to bear up to 10 tons per square foot, whereas organic fill or silt at the bottom of the chart or soft clay is able only to withstand a bearing value of 1 ton per square foot. So knowing something about the stability and bearing capacity of the geologic material and the soil material upon which the development pattern is going to take place is very critical to understanding its suitability for different kinds of uses. We can see in these two photographs the implications of a soil or geologic material whose bearing capacity has been exceeded. In both situations, the foundation of the structure has settled as a result of failure of the underlying geologic or soil material and resulting in significant structural damage to the house. So insufficient bearing capacity results oftentimes in structural failure. Another property, engineering property, is called shrink swell capacity. This is especially true in soils that have a lot of clay. Clay particles tend to expand when they become very wet, and they tend to compact when they become very dry. So they literally change size. And you can see the effects of that in the diagram on the left, where you can see what looks like mud that is cracked. And the mud consists of a lot of clay particles. And these clay particles, these particular particles, have a very high shrink swell capacity. And so as they have dried out from a saturated condition, the space between the clay particles has increased in size, causing the cracking that you see, both the large cracks as well as the smaller cracks within the individual piece of the clay. And so when the shrink swell potential of clay plays out, it tends to move. Things tend to move around within the soil. So things that is foundations or pipes that are contained within soils having a high shrink swell capacity move around and are damaged. Now, not all clay has a high shrink swell capacity, so one needs to know something about the soil and the clay content of that soil and the nature of that clay content relative to shrink swell capacity, and treat the underlying material differently depending upon whether the clay particles have a high shrink swell capacity or a low shrink swell capacity. Also, corrosion is an important property associated with soils. The chemical characteristics of soils can create significant erosion problems for steel, as is the case of the corrosion of the pipe on the left-hand side, or corrosion of concrete, as we see on the right-hand side. So understanding the corrosive properties, in addition to understanding shrink swell capacities of soil, becomes a very critical dimension to understanding its suitability for construction. Potential frost action is the notion of what happens to the soil when it undergoes freezing and thawing. Water reaches its greatest density at 4 degrees Celsius. As it cools below 4 degrees Celsius, it's freezing, and it expands in size. And similarly, as it warms up from 4 degrees Celsius, it expands in size. And so this freezing and thawing of water within soil then has a tendency to cause the soil to expand or contract. And in Minnesota, don't you know, we know all about these because we have these things in the road called potholes. And potholes are simply a function of water getting into the paving material or into the material immediately underneath the paving material, freezing and then thawing, and then freezing and then thawing, and then freezing and then thawing. And every time it goes through that freeze-thaw cycle, it tends to break up a little bit more of the particle matter contained within the pavement or the underburden. We can see in the upper right-hand diagram, there's a fairly large boulder that has significant cracks within it. And these cracks are attributable to freeze-thaw action of water residing within the rock itself. The image at the lower right-hand side shows foundation failure associated with freeze-thaw cycle damaging the foundation of a structure. So understanding the potential frost action is the property that it's called. Understanding potential frost action of a soil becomes critical to understanding its suitability for different kinds of development. The natural angle of repose refers to the maximum angle measured on a slope when the soil material is stable and at rest. When we exceed this angle of repose, natural angle of repose, the slope of the soil will fail. And in the left-hand diagram, we can see an example of a soil that has a natural angle of repose of 36%, and another soil that has a natural angle of repose of 36 degrees, and another that has a natural angle of repose of 27 degrees. If we try to make a 27-degree natural angle of soil repose into a 36-degree slope, this slope is going to fail simply because that is steeper than the inherent capacity of the soil to support. We can see that the image in the lower left, where the natural angle of repose has been exceeded and the slope has failed. This property becomes especially important when we are talking about areas that need to have steep slope for one reason or another. For example, a ditch along a highway needs to have a slope in order to create drainage ditches to carry water away from the highway. Well, different soils through which the highway travels may have different angles of repose. One soil may have a very steep angle of repose, as we see in the upper diagram, and the bottom soil may have a very shallow natural angle of repose. And if we try to make the soil that has a very shallow angle of repose do an angle of repose that is characteristic of the top soil, we're going to continue to have failure of the slopes on the ditch and eventually failure of the roadway itself. Erodibility factors affect the susceptibility of the soil to sheet and rill erosion. There are two factors that are associated. Soil particles are more finely grained, and it becomes higher when soil particles are more angular in shape as opposed to rounded in shape. So knowing something about the texture of the soil, how finely grained the texture is, and knowing something about the particle shape helps us get a better understanding of the propensity of that soil to erode. The T factor is the maximum average soil loss that can be sustained without affecting crop productivity over time. So we can take these two factors and divide the K factor by the T factor and come up with a ratio of K divided by T, which gives us a sense of the soil fragility. The higher the ratio of K over T, the more fragile the soil is. And with flowing water and wind able to detach and transport the deposit particulate matter via the erosion cycle, where we have particle detachment through raindrop splash, other moving particles, and particle transportation through moving water or wind. As we've talked about earlier, raindrop splashes is the tendency for falling raindrops when they hit the surface of the land to splash soil particles off of the land surface into adjacent surfaces. Once they are detached through raindrop splash and water is moving across the soil, the particles begin to bounce off of the bottom and bounce off of the walls of the channel through which they're flowing, causing channel erosion and incision of the bottom. Detachment of particles from upland areas and deposition into bottomland areas is what soil erosion is all about. And this is greater than in soils that have a higher fragility index. The solution to this, of course, is to keep the soil covered with plant material to slow down water and wind and to infiltrate moisture as much as possible. We see on the left-hand side a diagram of a prairie planting. The prairie planting has a very dense canopy. The very dense canopy does two things. First of all, it intercepts raindrops, preventing raindrop splash from from detaching soil particles in the first place. Secondly, the very dense root structure promotes water to infiltrate into the soil quite readily, flowing down through the root tendrils as they penetrate soil structure. And then also the very dense foliage cover of the canopy also prevents erosion as water flows across the surface. In a forest context, we get raindrop splash interception through multiple canopy layers. We have the canopy associated with the overstory of the forest canopy, the understory of the forest canopy, the shrub layer of the soil canopy. So the greater the number of layers, of vegetative layers within the vegetative community, the greater the raindrop interception, the lower the rate of raindrop splash. And also then the higher the density of vegetation, as is true in a prairie planting, the greater the tendency of the soil to be held in place by plant roots. Also, we can talk in agricultural contexts about using harvestable biomass to line waterways as a strategy for reducing uh, water flowing across the landscape coming off of planted fields, and slowing down that velocity so that whatever erosion comes off of the field is deposited in the harvestable biomass filter strip before it's deposited into the adjacent water body. We can talk about the same concepts in handling fields during wintertime, maintaining some kind of a continuous cover crop throughout the winter when the soil is bare, and in late fall and early spring when we get a lot of heavy rainfall, making sure that the soil has some kind of a cover on it to prevent soil erosion during these high rainfall periods. Agricultural terraces become another strategy for reducing runoff across agricultural landscapes, slowing down the velocity of water, retaining water on the landscape itself. Contour strip cropping does the same thing. The contour strips run parallel to the topographic contour, and the continuous cover slows down the runoff velocity. Grassed waterways become another strategy for preventing soil erosion, whether they're used in an agricultural context, such as you see here, where the continuous cover of the grass, perennial cover of the grass, tends to slow down flow of water, tends to trap sediment before it's discharged into surface water bodies.